Another example of an idempotent operation in distributed systems is a broadcast operation. Like, for example, in WhatsApp, when one client broadcasts their online or their offline status to a server, as well as an append operation when certain items are appended, let's say, to a file. We also talked about how the use of session IDs and crash logs allow us to recover from various faults, and also give some fault tolerance to the distributed system. In a session ID, we talked how it was made out of three IDs: the client ID, the server ID, and the request ID, where the client and the server IDs are just counters that count how many times the client or the server respectively has crashed and has recovered from their faults. The purpose of this is, of course, to realize that both the clients and the servers can crash, and that the server and as well as the client, they need to know which request they're dealing with and from which server, from which client respectively the request or the response comes. We talked about retry and fail, where after a timeout we retry again the same operation. And we also talked about how one way to ensure that at least some fault tolerance is present in the system is through the use of replication. Either the use of replication of data items across various servers, or the use of replication with the idea that we're replicating functionality and we're distributing it across various servers. And an example where replication happens is the Google file system. Now, what I'm telling you right now is based on an old version of the Google file system. Things have changed, and Google currently, if I'm not mistaken, doesn't use GFS anymore. We talked about how there are a lot of failures within the Google system because it's made out of commodity hardware. We also talked about how within Google there are some big data workloads, and these workloads are generated by search, ads, web analytics, MapReduce, and so on. There's also an additional operation, which is a record append, which is very frequent at Google because there's a lot of logging done of user activity and site traffic. Now, for an append, the order doesn't matter, but of course, the operation in itself must be atomic, and one must make sure that concurrency is respected. So, the way the GFS is designed is that there's, within a GFS cluster, there's one master, and there are many chunk servers. And these many chunk servers are accessed by many clients. And the access is done through the master, in the sense that the master communicates some vital information to the clients, but then the clients communicate directly with the chunk servers. A file is divided into fixed size chunks. These chunks are stored at various chunk servers, and they're replicated usually across 3 chunk servers. The master just keeps track of the metadata. So as we can see here, the second part of file 1, so chunk 2 of file 1, is replicated across 3 chunk servers. And the first part, for example, is replicated across the first 2 chunk servers. As I said, the master holds the metadata. The application or the clients initially communicate with the master to get that metadata, and then directly with the chunk servers. The master, because it's really not that involved, it's not a bottleneck, but if you notice in this diagram, there are still nevertheless some shadow masters. So if the main master dies, then there should be other masters that can take control. This is basically saying what I just said before, except that you have thicker lines for data messages and skinnier lines for control messages. The read operation is fairly simple because the client will get information from the master, and then it will just read from a particular replica. The write is a bit more complicated because one needs to ensure that the data is replicated across all replicas. And in here, what we see is after the client receives from the master the response of the primary and the location of all the other replicas, then the client, it's the responsibility of the client to push the data to the replicas. Once that has happened, so once all replicas have received that data, they will acknowledge receiving the data, and then the client will send a write request to the primary replica. And there's this idea of a primary replica here. Now, of course, there needs to be some decision as to where replicas will be placed. Usually, we need to maximize data reliability and availability, and also the utilization of the network bandwidth. We shouldn't put replicas we shouldn't spread them just across machines, because we saw how a rack failure can bring down all the machines within that rack. So we should try to spread replicas across racks to ensure that they survive. And of course, the chunk servers are re-replicated as soon as the number of replicas falls below a goal. Now, within distributed systems, a lot of decisions have to be made with respect to a lot of things. For example, the system state, whether the system is crashing or not crashing. And in order to decide on this, there's something that is called a distributed snapshot algorithm. The status and the location of a data item, as well as who responds to a particular query. This is dealt with by protocols such as Paxos. Whether transactions can be committed, as well as who's allowed to enter a critical section. Whether transactions can be committed, these are dealt with by protocols such as Paxos, two-phase commit, or three-phase commit. Now, all of these protocols must ensure that they reach whatever it is that they're supposed to reach. So, for example, with Paxos, we'll be able to determine whether a distributed transaction can be committed. But also the fact that these algorithms are resilient to failures. So if a number of entities within the distributed system fail, or if the network between them fails, these protocol will still reach a decision. So an example of agreement in distributed system is one when entities decide who is allowed to enter a critical section. So a critical section is a section of a code or a section of a distributed system in which only one process is allowed to work. The way this usually works is that each process will execute a loop, they'll perform local operations, they'll request access to a critical section, they'll perform some critical section operations, and then they'll leave the critical section and perform local operations afterwards. As an example, think about how we may have different processes and different entities trying to write to a file that is on a particular file server. Now, we're looking at ensuring that safety happens, so at most one process holds the lock at any time, that the protocol or that the algorithm allows for progress, so if nobody holds the lock, if anybody wants to enter the critical section, then they'll enter, and that processes will not wait indefinitely and they will acquire the locks in the order of request. This is called fairness. Of course, you also have some performance goals. You want to minimize the message traffic, you want to minimize the synchronization delay, and you also have some assumptions. The network is reliable, but it is asynchronous, and of course, the processes may fail at any time. So our plan is this. Before we enter the critical section, the process must obtain permission from others. This is called a safety. This will allow us to obtain safety. When exiting a critical section, the process must let the others know that it has finished. This will give us liveness. And the process should allow others that have asked for permission earlier to enter the critical section. This is called fairness. So we want to build an algorithm that allows processes to enter a critical section and that has these three properties and deals well with failures. And what we did in class is we came up with a number of algorithms. The most popular one was the centralized lock server, where there was a lock server somewhere that was the central piece of this algorithm, and through this lock server, all the decisions were made. So in order to enter a critical section, the process would send a request to a central server, wait for permission. Once that permission is received, enter the critical section, send a release once they're done. The server will log all requests in a queue and will send OK to processes at the head of the queue. Now, of course, this is very simple. There are only three messages required, which is basically sending the request, receiving permission, and telling the centralized log server that they have exited. However, this is, of course, a single point of failure, because if the centralized log server dies, then the entire algorithm or protocol crumbles. It doesn't achieve fairness, because while the server itself logs all requests in a queue, this only guarantees that those requests are served in the order in which they arrive at the server, not the order, and this is, let me show you what fairness means, not in the order in which they have requested. And of course, because the network is not performing as we want, this can happen in the sense that, let's say, process 1 has one request R1 right now, process 2 has request R2 several minutes afterwards, but because of the network, request R2 arrives first at the centralized log server, followed by request R1. This means that these requests will be queued first R2, then R1, and of course this doesn't give us fairness. Now, of course, also, if the centralized log server is not predefined by a sysadmin, then we need to elect one, which means that again we need to agree on something, which means that we need to have an agreement protocol again. Another way for dealing with access to critical section is by using a ring-based algorithm. So there's a token that processes pass around the ring. Processes can enter the critical section only if they hold a token. The problems, of course, is that this is not in order. You can't enter the critical section when you want to, but only when you have received the token. There's a long synchronization delay because you need to wait for n-1 messages. And it is unreliable because if any of these processes fail, then boom, the entire thing goes down. And of course, you can improve this by piggybacking on the token by saying the time of the earliest known outstanding request. And this should allow processes to know if their request is the most outstanding. So this is a summary of all algorithms. I didn't talk about the Lamport algorithm. It is fairly better with the synchronization delay, but it doesn't do so well with messages per entry and exit. Now, of course, there are some other algorithms, such as, for example, voting, where all the processes vote as to who should enter the critical section, and the process that has the majority enters. What the industry uses is a centralized algorithm. Google has Chubby and Yahoo has Zookeeper, but they use replication of the centralized log server for fault tolerance. The replicas will coordinate using voting, and the app writers must avoid, obviously, using the centralized log service as much as possible. And this, again, can be done because both Google and Yahoo employ the developers that use these centralized log servers. So these are not public domain. And and this is the last issue that I'm going to talk about, another important issue in distributed systems is time. We saw before how the time moment when something happens versus the time moment when a request arrives at a server will be different, and these will also influence the order of requests and so on. So timing is crucial in a distributed system. And I'm going to give you some examples. So let's say I have two databases which are replicas of each other, and they both contain information about my bank account. And let's say at time 10:05:23, this information is added to both databases, first to the first one on the left, then to the second one. And what this action currently does is it adds 10%, so I have some interest added to my accounts. At the same time, at an ATM closer to the second database, I add $100 to my account. And of course, this gets replicated and so on, but the question is here, which actions should be done first? Do I want the 10% first and then add the $100? Or do I add the $100 and then add the 10%? Of course, I would want the second case, but I think the bank might want the first case. Another example is a distributed make. So think about us having two computers, a faster computer, which is shown at the top, and a slower computer, which is shown at the bottom. And I'm going to do all my compiles on the faster computer and all my edits on the slower computer. Now, let's say at time 6:52, I have compiled my program and I have created the executable. Maybe I'm sending a message to computer 2, an edit happens, and then computer 2 sends a compile message, to computer 1. Now at this point in time, program C is annotated as having been edited at 6:50. However, the executable was created at time 6:52. So for all purposes, for the compilation and for the make folder, this program will not be compiled. Hello, what are you doing? Sorry about that. Boom, boom, boom. So this program will not be recompiled. So one of the most important things that I'm just going to leave this one here, that have been discovered and that have set the tone for distributed systems with respect to timing is that it is not the specific time moment at which a particular event happens that is important in a distributed system, but rather the order of events. So, if we can define a happen before order between all of these events, then we can establish a general order overall, and then we can decide which event happened before which other event, and then come up with a general order in which we can do things. So for example here, if we can say, well, okay, the executable has been created at computer 1, then a message has been sent to computer 2. Obviously, the time when the event of sending the message at computer 1 will happen before computer 2 receiving the message. Then an edit happens, again after this receipt of message, and then another send happens. So what happens now, if we just look at the order of events, we'll see that the editing of program.c has actually happened before the request to recompile. So therefore, we can recompile this program. Now, the way this happened before relationship is achieved or facilitated, I think facilitated. The way this happened before a relationship is facilitated in a distributed system is through the use of Lamport clocks or through the use of logical clocks. These logical clocks are just counters in the case of Lamport clocks. They're just simple counters of events that are happening at a process. So let's say in the case of, again with the animation, in the case of computer 2, we have one event at 6:49, another event at 6:50. So we have a counter that is at value 2 right now. For computer 1, we have one event at 6:52. We then have the send event at, let's say, 6:53. And then we have the receiving of the message from computer 1 at 6:55. So we have 3 events. Their counter is set to 3. And with a little bit of maths and with establishing happen before relationships. So for example, when we send a message, clearly the sending of the message has to happen before the receiving of the message because we haven't invented time machines yet. So with a little bit of maths and these sort of relationships, we are able in some systems or in some cases like here to establish a full order. In other cases, we only have partial orders of events, but even these partial orders are much more easier to use and allow us to get a better understanding of what events should be executed first than just using time. There are many types. So we have the Lamport timestamps, which are those counters that I talked to you about. We have vector clocks, which are basically Lamport timestamps that have been put in an array with the Lamport timestamp for each of the processes in the system. And we also have matrix clocks. Now I stopped here during the lecture, so I will stop here at naming in the podcast as well, because I do not want us to get confused. Naming in itself, although it is in the lecture slides, is not part of the assessment for the course, and it's not part of our discussion. Great, that's it. Thank you.